Well, I'd like to talk about the cooling dynamics of the hot cluster ions. So this is somewhat slightly complicated story. So I'd like to start with the conclusion, the most important result. So that is the unstable, I mean the above detachment threshold, unstable ions are stabilized efficiently without the collision process. So we can prepare the highly excited anions by collision or photoexcitation or simply electron attachment to the neutrals. So we can get the vibrationally highly excited ions fairly above the detachment threshold. And so for small molecules, the thermal detachment rate is very fast. So the ions are not stable. So we need extra particle to remove the excess energy. But it's not the case for even-numbered carbon clusters. The highly excited carbon clusters are stable by itself. He does not need the third body because it cooled down very efficiently by electronic radiative cooling. So now we come to realize this is not special for these carbon clusters. And so we must see such the first radiative cooling for various ions. And so if the system is highly isolated, so we have to be very careful for such electronic cooling. Otherwise, we surely underestimate the effect of the radiative cooling. So this is the outline. So I'd like to start with some words for the carbon cluster, small one. It's a chain form. And the carbon cluster, and with the polyenes, the hydrogen, one of the end. And the relevant molecular process, internal conversion and IIC, it's an inverse process, and delayed electron detachment or radiative cooling, I like to mention. And the experiment we are doing is the laser merging study using electron ion storage ring. And we conducted the simulations based on this purely statistical model. In fact, this is the compilation of several works already published. But in the last 2 minutes, I'd like to show some new result. And I think it's even more important. I put it in the last. So this is the electronic structure of the carbon cluster. I'd like to start with the neutrals. So for odd-numbered clusters, for example, C3, there is 4 pi electrons which fully occupy the pi orbital. So it's a singlet in ground state. But for even-numbered clusters, for example, C4, there is 6 pi electrons. So it partially occupies the highest molecular orbital. So it's a triplet in its ground state. So it's a big difference. Naturally, for ions, there's a big difference for even and odd-numbered clusters. For example, C4 minus, there's some electronic excited state just below the detachment threshold. There's only one. But for C6 minus, the detachment threshold is much higher because the electron affinity is large. And you can see 2 dipole allowed electronic state fairly below the detachment threshold. So this is a big difference. So this is not carbon cluster, but very similar. The polyenes, 1 hydrogen at the end. And the polyene anions are actually found in space. And the people believe these polyene anions are produced by two-body collision of the neutral polyene and the electrons. It forms the transient highly excited ions. And this is unstable. So to get a stable anions, so there's competition of the radiative cooling and detachment. So the radiative cooling process is the very important issue for industrial chemistry. So this is it's a photoexcitation and de-excitation cycle for highly isolated system. So we can excite the anions by photons to electronic excited state by UV or visible photons. And sometimes it emits electrons, sometimes it emits photons. But for carbon clusters, the internal conversion is very fast. So the electronic energy is converted to the vibrational energy quickly. And we are interested in what happens after the internal conversion, after the thermalization. And so the highly excited, vibrationally excited electronic ground state, the ion, it gives the thermal electrons. So this is the delayed detachment. And it gradually cools down by vibrational radiative cooling. So it's a really slow process. It's a millisecond time scale. So we need some ion storage device. So for carbon clusters, the internal conversion process is studied by Newmark and co-workers by very nice pump and probe experiment. And so they reported the IC rate. It's very fast, picosecond time scale. So even in the nanosecond time, pulses, the internal energy, electronic energy, is transferred to the vibrational energy before the next photon comes. So, for example, 3-photon excitation is not like the vertical stacking of 3 photons. It's the independent 3 same transitions just to heat the ions. This is a good situation for us because we play with the storage ring, so we observe the slow process, at least a microsecond or slower. So all the phenomena we are observing is after the internal conversions. So it makes the situation simple. But the highly isolated system, the inverse process, the inverse internal conversion, makes the situation a little bit complicated. So the summarization is the sharing of the energy by statistical way. And the energy acceptor is not necessary to be the vibration. Electronic energy can be acceptor. So there is some equilibrium of the ground and electronic excited state. And the IC and inverse process IIC is forward and backward reaction in this equilibrium. Of course, IIC, this is the process from the vibrational energy to electronic energy. This is much less likely because the state density here is here and here is much different. But still, the probability is not 0. And once the electronic state is thermally populated, so it may emit photons. So this is the not normal photons. So we call it recurrent fluorescence to distinguish normal direct photons. And once it works, it highly accelerates the radiative cooling process. And RF process needs low lying. Low lying means the fairly below detachment threshold. Dipole are the electronic state. So you already know the even numbered cluster, this is yes, and odd numbered cluster, this is no. So now I'd like to move to the experiment. And so we are playing with the electrostatic ion storage ring in our university. This is the 8-meter storage ring and with a good vacuum. And clusters are produced by laser ablation or cesium sputter source. And so we get the hot ions. We don't use the cooling gas. And these ions are accelerated to 15 or 20 kilo electron volt and injected to the ring as a pulse beam. So the pulse bunch, ion bunch in the ring is something like this. And with the proper timing, we shine the laser to excite the ions. And then, so this is the excitation, but in fact, this is the heating. And then we see the neutrals, the detachment product, using the microchannel plate here or here. And the very first peak from the microchannel plate here involves the very first detachment process. So the two-photon process may contribute to the very first peak, but for other old peak, it's purely due to the single photon process. So, and the detachment rate is the function of the internal energy. Of course, it's faster for energetic ions. So during the storage, the high energy component is preferentially removed from the storage ring. So this is kind of cooling, so we call it the depression cooling. And relative cooling just shifts the population to downward. So relative cooling does not yield neutrals. So we detect the neutrals, so we cannot observe the relative cooling process directly, but we see the neutrals, depression cooling process. So situation is something like this. We have hot ions, and so the detachment, and usually vibrational relative cooling process is very slow. So we see depression cooling, and the relative cooling is just the perturbation of the detachment. But if the electronic process works, it's very fast. So this process quickly eliminates the hot ions. So the detachment yield also decreases so quickly. This is indeed we observe for carbon clusters and polyins. Here you can see the polyene anion, the decay after the photoexcitation. So it decays very slowly, and this is a sign of depression cooling. But you can see for C6 minus, so it's very fast, so you don't see actually how fast it is. And the decay profile is near exponential. So here you cannot see what is, so it is really exponential, but this is confirmed later by the Weissman group. And so here you can see electronic cooling works for C6 minus, but does not work for C6H minus. And we can simulate the process by calculating the detachment rate as a function of energy by employing the detail balance and the vibration and the electronic cooling rate by the population times the transition probability gives the rate constant of the cooling. So by using rate constant, so we simulate all the process. So here the result, so the dot shows the experiment, and the lines show the simulations. You can see big difference for even and odd numbered clusters. So for the C4 minus, for example, just during 2 revolutions in the ring, so the neutral yield decreased 3 orders of magnitude. So it's a very quickly decreased. And also for C6 minus, a 2 order of magnitude decreased. But for even odd numbered clusters, even after 10 revolutions, so we can see the detachment product. And simulation fairly agree with the experiment. And now we understand, so for even numbered clusters, electronic cooling works. And for odd numbered clusters, it does not work. Now let me go back to the experiment. So we excite the laser. We excite the ion by the laser here and detect the neutral here. So here were some one revolution later. Anyway, so we selectively detect the ion with the specific lifetime, specific KD, detachment rate. And the detachment rate is a sharp function of the internal energy because this is a small clusters. So the rate is converted to the energy. So the energy range is very small, just above the detachment threshold. So we call it the energy window for the detection, and denoted by E0. This is quite useful. So here you can see the E0, some just above the detachment threshold. And so we can survey the population of the ions and how the changes as a function of the storage time. So we excite by the photon energy h nu, and we only observed after excitation the E0 guys. So we measure the population at this energy before photoexcitation. So if the peak is high energy side of this energy, the cooling makes the better overlap of the peak and population and this energy region. So we can see the increase of the signal neutral yield and then see decrease. If we use the red light, so here is the peak and then simply going down. And if we use the blue light, so it initially very low energy, but we sample the number of the population here, and then the storage makes the increase of the population here. So we may observe the increase of the neutrals as a function of the storage time. So this is indeed observed for the carbon clusters. You can see for C5 plus, C5 minus, and C7 minus, the excitation by red light, it peaks at shorter storage time. And excitation by blue light, it samples lower energy side, it peaks later, or if we sample very low energy, it's simply going up and stay here. For C6 minus, it just decreased because C6 minus cools so fast. So at the beginning of the storage, it's already the peak is lower side of the energy window, minus h nu. And the further cooling lowers the overlap. So we can see just a decrease. For C4 minus, the decay is much faster. It's a full scale is just 6-8 milliseconds. Others are 100 or 50 something. But anyway, it's much faster for C4 minus. And you can see the storage time dependence is nearly exponential. And the situation is something like this. Here we measure the population at the energy window. And for vibrational cooling, so the population is determined by the balance of the coming in and going out. So the function, the time evolution of this population is somewhat strange shape of going up and going down sometimes. But for electrolytic cooling case, the energy removed by single transition is really large. So situation is something like this. So there's no source to coming in. So it's simply going out, going out. So in that case, the neutral yield means the population here is a single exponential decay. This is indeed we observed, and by changing the wavelength, so we can sample the various energy level, and so you can see the rapid change of the slope. And Now we can show you how the electronic cooling works. Above the detachment threshold here, CX transition very efficiently cools the ions. It's highly suppress the detachment here. At the lower energy side, but CX transition does not work, but still BX transition cool efficiently before it going down to the onset of the B state. So now we know such situation can be found for various ions, for also the various molecules. And this is possible. So if there is some threshold, it can be detachment or dissociation in any threshold. And below threshold, the highly vibrationally excited molecules are stable. And there may be some electronic excited state below the detachment or any threshold. In that case, the electronic cooling must work. So let me go back to the conclusion. So electronic cooling is not an unusual phenomenon for highly isolated hot molecules. Well, now I'd like to go to the new one. So there is electronic transition. There's some recurrent fluorescence photons. So we should try to measure this photon. This is actually the hot topics in 35 years before. And at that time, the infrared laser is available. So people try to get some visible photons by infrared multiphoton process. But unfortunately, at that time, they cannot get conclusive evidence for the recurrent fluorescence photons. But now it's a chance. You know, C6 minus, for example, is the summarized very quickly. And so we know it gives the photons, recurrent fluorescence photons. So we put some photodetector here and try to get the photon around 600 nanometers. We shine the laser here and detect here. This is the point, because we already know that the internal conversion is very fast. So if the photon at 600 nanometers is detected here, this must be recurrent fluorescence photons. So I like to show the result here. You can see two peaks. It's not very strong. It's just 30 count after 30-hour accumulation. So the count rate is just 1 count per hour. And this huge signal is the scatter light. But it's quite clear there's two peaks. And the timing is completely agree with the circulation of C6 minus. And if we change the laser timing slightly to irradiate the laser when the beam ion is opposite side, we see nothing. So now we can safely conclude this is recurrent fluorescence photons. And so this is the first detection with the laser-induced recurrent fluorescence photons. And so finally, I like to show the quarkers. Of course, these works heavily rely on the hard workers of the Japanese people. And so here, the quarker, this is the cooperative work of the TMU and the Riken Institute and the Gothenburg University. And the photos people who attend this conference. Thank you very much.